Hello everyone, my name is Trevor Smith. I'll be presenting active cooperative localization of swarm robots using adaptive Boids rules. In this presentation, I'll be going over the motivation for this research, localization, Boids rules, adaptive Boids rules, and the results, conclusions, and future work of this study. So for the motivation, multi-robot systems is an emerging field in robotics. However, due to the exponential cost, these systems mainly consist of simple robots with poor sensors. Thus, complex perception, such as localization, is very difficult for these simple agents. So why localization? Localization is essential for basic robot tasks such as decision making, map making, and path planning, along with other high-level functions. So if a robot's localization is poor, it's often confused and doesn't know what to do next. So the scenario we used for testing is that each robot has a random goal location as indicated by the gold stars. They perform range and bearing estimates to other robots. They have wheel odometry indicated by the green path and have a home base with a known location. Localization. So is the process of determining the position of the robot. It includes a state as shown by the asterisks around each agent in the center of each ellipse, which is the covariance and is a measure of the uncertainty. Each ellipse shows a 95% confidence interval of where the robot is. So by combining a predicted state, which shows anytime the ellipse gets bigger as the robot is taking its prediction step, which increases uncertainty, and measurement, so anytime you see an ellipse decrease, as just right there, is a measurement by covariance intersection, which reduces the uncertainty. So for the prediction state is done by dead reckoning, which is the summation of all path legs is done to predict the current position. So if you have path leg 1 and path leg 2, if you sum them together, you'll get the green line, which is the estimated position. Next we have covariance intersection, which serves as the measurement. So it receives multiple estimates of the location shown by the gold, blue, and green ellipses, and then it fuses them together based off of their uncertainty to get an improved estimate of the state shown in red. Boids rules were inspired by the flocking patterns of birds, and they first separate from each other to a safe distance, then they align their headings together for the group, and then they cohere together to form groups. And if these are tuned properly, you can see nice emergent behavior as shown in this video. So our hypothesis is that if we incorporate Boids rules with localization estimates, we will then get a better localization estimate. So how we adapted Boids rules is we included a home and goal rule, which point towards how the agents head towards home or head towards their goal respectively. And now every rule is now influenced by the density of the robot swarm, the mean error between the estimated and predicted positions, the covariance, the distance to home, and the distance to the goal. So we wanted the alignment to increase as the robot density increased to aid with obstacle avoidance, along with as the mean error increased. That way, if the robots became lost, they could follow another robot home. And thus, as the distance to home decreased, we wanted the alignment to increase to also help with obstacle avoidance and help them get in and out of home as fast as possible. For cohesion, we wanted to increase as the mean error and covariance increased. So as our localization estimate became poor, we want the agents to group together. That way they can perform more measurements on each other and decrease their uncertainty. We also wanted a cohesion to increase as the distance to home increased, because the further we were for home, the more likely your estimate is poor, and thus we wanted the agents to group up together. Note that the distance to goal portion for cohesion will actually turn off this home portion if it's near the goal, allowing the robot to head towards the goal if it is close to it. First, we wanted separation to increase, kind of inverse to cohesion, where the mean error and covariance were low. That way they could just head directly towards their goals and separate from other groups. As the distance to home decreased, this is kind of to help with obstacle avoidance again, where they're near home and kind of clustered to try and spread out a little bit more. And same with the distance to goal. We wanted the separation increase as the distance to goal got farther away. That way, if they're in a group headed the wrong direction, they can actually break out of it and head towards their goal. We wanted the home gain to increase as the mean error and covariance increased. That way, the agents will start heading home if they need an update and their localization is poor. And the distance to home to decrease. As the distance home decreases, we wanted the home to increase. That way, if the robots are near home, they would head home and to get an update. However, the distance to the goal will actually turn off this portion. That way, if there's a goal near home, it can still reach it and not just get sucked into home every time. Inverse to home goal will increase as the mean error and covariance decrease. That way, when the robots are more suited to reach their goals with low uncertainty in their localization, they can head towards it easier. Along with, as the distance to the goal decreases, we want the goal to increase. So if it's near the goal, it'll reach it. And however, this gets turned off if the distance to home is very small. That way the agents can return home for an update before they reach their goal. So all those parameters were formulated into these 5 equations that are used. Note that they're all non-dimensionalized. That way they can be scaled to any sized robot and or environment. And here we see we're using sigmoid functions to turn off those different components. So here is a direct comparison of the waypoint only baseline and our proposed adaptive boids. You can see the boids, or the waypoint only, reaching their goals a little bit faster than the adaptive boids. This is because they're directly heading towards them. But you can also notice the adaptive boids, on average, has smaller ellipses than the waypoint only. And also note that the waypoint tends to form straighter lines when moving, while boids rules tend to be a little bit more curved and wavy as they try to cohere together to get better updates. So the results is our proposed blue was at about 50% better covariance than the baseline red. So it's about 50% more certain in its location. A note that the asterisks indicate dead reckoning only paths. So where each robot would only use its own information along with the home base. And then for covariance intersection shown by the triangles. For covariance intersection, you can actually see a diminishing returns as the number of agents increase. This is because as these agents increase, the local density of robots increases, thus they're more likely to bump into other agents and don't need to directly seek each other out as much. For the results, the proposed blue had about 1.5 less goals reached than the baseline red. This is due to those path deviations taking time, thus they're not able to reach as many goals as directly heading towards them. So overall, the proposed blue algorithm had approximately 30% less cost than the baseline red. This is based off of this cost function here. So in conclusion, by including the adaptive Boids rules, the robots were encouraged to actively cooperate to improve their localization estimates as necessary. Thus, the localization error was reduced by about 50%, at the cost of about 1.5 less goals being reached. For the future work, we will have the agents stop to become landmarks, which is very beneficial for localization, as it will remove IMU bias, create points far from home with low uncertainty of localization, and construct roads for the agents to follow, as shown by the figure to the right. This study was funded by the National Science Foundation under a NSF Award 185-1815, and we'd also like to thank Dr. Yu and Dr. Pereira for their contributions in developing the concepts included in this project. And these are our references used, and for any questions, feel free to let me know. Thank you all for your time, and have a nice day.